Next up in our tutorial is overfitting and underfitting. Overfitting and underfitting are two things that can go wrong when you train a machine learning model. So let's look at what those are. Let's start with underfitting. Underfitting means that your model does not fit your training data well. And this happens when the model that you're fitting is too simple and it can't capture really any pattern in the training data. On the flip side, you have overfitting, which means that the model does very well in the training data, but it doesn't generalize to the test data, meaning it has essentially just remembered the training data and it hasn't really found any pattern in it. Let's look at an example in the regression case. Here we have one feature and we have 9 training instances, 10 training instances, which are represented by these blue dots. So the true pattern is basically the green curve. And in this example here, a straight line, so linear regression, just with one feature, has been fit. And you can see that it very much deviates from the true pattern. And the training error is very large. And this essentially means that the predictor or your model can't capture any pattern at all. The model is too simple. The other extreme is this plot here. Here, a polynomial has been fit with degree 9, which means that polynomial terms have been included in a linear regression up to degree 9, so x to the power of 9. And you can see here that the training error goes to 0. However, once again, you're not really capturing the pattern in the green line. As you can see here on the right-hand side, this curve will actually shoot up to infinity, and on the left-hand side it will shoot down to negative infinity. And consequently, your test set error will be quite high because you're capturing the noise in the training data. What you want is something in the middle. This is a cubic polynomial, so this has terms x, x squared, and x cubed, and it best approximates the green line. So the training error is not exactly equal to 0. You will have some training error, but at the same time, it does manage to capture the pattern. Let's have a look at the classification case. So we have two classes, and if you fit a logistic regression, let's say, with a linear decision boundary, so here we just have two features, you will get a straight line that produces a lot of errors. So here you have x's on the wrong side, and here you have circles on the wrong side. Once again, your training error is too high because you're not able to capture any pattern in the data, or very little of the pattern. Once again, the other extreme. Here, this could be a logistic regression with a lot of features. So you could have included x1 squared, x2 squared, x1 times x2, and maybe even cube terms to fit this pattern. And although there are actually no training errors, there's 0 training errors, this is not really the pattern that we want to capture. This seems to be noise that is being remembered, essentially. What you want is something in the middle. Again, you want a model that's not too simple, but also not too complicated. There's some training error, similar to these two x's here, but we do manage to capture what should be captured, the essential pattern of the data. So what's the relationship between training error and test error compared to overfitting and underfitting? Generally speaking, if you have a simple model, your training error will be quite high because you can't capture any pattern, and of course also your test error or your generalization error. On the other hand, if your model is very complicated, let's say it uses lots of features, or it's a very complicated neural network, which we haven't spoken about, your training error can actually be driven down to 0. However, your generalization error, your test error, or your test loss, I'm using these terms interchangeably here, will actually not be very good because, again, you're just capturing the noise in the training data. You're not really remembering. Sorry, you're remembering the training data, but you're not capturing the pattern. You're not really learning. What you want is something in the middle, because at the end of the day, you're interested in the generalization error or the test error, and you can achieve this optimal by finding a model that's not too simple, that doesn't underfit, and also not too complicated, that doesn't overfit. So how do you do this? Well, first, to prevent underfitting, you want to use enough features and you want to use an adequate model. So sometimes linear regression would cut it. You might need something more complicated. You also want to train your model for long enough. Sometimes, especially if you train neural networks, you can stop training early. You want to train long enough in order to minimize the cost function as well as you can. How do you prevent overfitting? Well, don't make the model complicated. Don't use too many features if you don't need them. Don't use a neural network if you don't need it. You can also regularize the model, which is essentially a way of making sure that the parameters that are being fit in the model are not too large, which tends to make the model simpler.